Good afternoon. My name is Dionne Ibarra. I'm a PhD student at the George Washington University. And today I will talk to you about on framing changes of links in three manifolds. This is joint work with Ria Bakshi, Gabriel Montoya Vega, Joseph Petitsky, and Deborah Weeks. So this is the outline of my talk. I will start with preliminaries. Then I will state the main result and illustrate the Dirac trick. Next, I will formulate our main result in the language of skein modules, starting with the framing skein module, Kaufman bracket skein module, where we will talk about spin-twisted homology, and then Q homology skein module. We will end with a diagram summarizing the propositions for each skein module. So first I will define den homeomorphisms on three manifolds. So we're going to let M be a three manifold, F a connected surface, such that F times an interval and the boundary of F times an interval are contained in the manifold and the boundary of the manifold. We have the extra condition that the surface times the interval intersected by the boundary of the manifold is equal to the boundary of the surface times the interval. For t between 0 and 1, we let phi of t be a continuous family of homeomorphisms of the surface, such that phi 0 and phi 1 are both equal to the identity on the surface. In this way, we can define den homeomorphism. So we use phi of t when the element is in the surface times the interval. Otherwise, it is the identity on the manifold. Below, we have a theorem by Maculo. This theorem is vital to the proof of our main result. It states that if a compact orientable manifold, three manifold, which admits a homeomorphism, which is a composition of den twists on the boundary of the manifold, then there is a collection of disjoint embedded disks and analy in the manifold, such that each of those boundary circles is isotopic to one of the simple closed curves. A manifold is called parallelizable if the tangent bundle of the manifold is trivial. A theorem by Stifel states that every three manifold is parallelizable. So we view spin structure as a homotopy class of parallelizations. And we use this to construct a homomorphism between the first homology of the manifold with Z2 coefficient and Z2. So we choose a parallelization of the three manifold, then identify the spin structure with the first cohomology of the manifold with Z2 coefficient. By the universal coefficient theorem, the first cohomology of the manifold with Z2 coefficient is isomorphic to the group of homomorphisms between the first homology of the manifold with Z2 coefficient and Z2. Each frame knot in the manifold represents an element of the first homology of the manifold. By using the parallelization of the manifold, we can map this knot to an element of Z2. And this is our homomorphism. So now we are ready to move on to our main result. We will let M be a compact oriented three manifold and L be a frame link embedded in M. Then the only way of changing the framing of the link by ambient isotopy while preserving the underlying unframed link is when M has a properly embedded non-separating two-sphere. And either the underlying unframed link intersects the non-separating two-sphere transversely exactly once, or the underlying unframed link intersects the non-separating two-sphere transversely in 2 points, each point belonging to a different component of the link. The framing is changed by a composition of even powers of den homeomorphisms along the disjoint union of two spheres, satisfying condition 1 and 2. So we will show the change in framing using the direct trick. So this is an illustration of the classical direct trick. Here we have a two-sphere and a link intersecting the two-sphere in exactly 1 point. So notice this is the sequence of isotopy. Here we go under and then over, and then we can just pull the strand tight, and you can see that the link has changed by +2, or the framing of the link has changed by +2. This is for case 1. So for case 2, we have a link that intersects the non-separating two-sphere in exactly 2 points, where each point is from a different component. So here, the red component will have the same sequence of isotopy as before. And notice for the green, it's slightly different. So here, instead of going under, for the green component, we will go over. And then here, instead of over, we go under. Once we pull the strands tight, you can see that the first component, the framing changes by +2. And for the second component, the framing changes by -2. So notice that if this component, or if these two components were the same component, then the framing would not have changed. A quick summary of the proof of our main result. We use McCullough's theorem to first prove that the only way of changing the framing by ambient isotopy is if there exists a properly embedded non-separating two-sphere with these two conditions. Then we use spin structure and the homomorphism that I explained before to show that the change in framing can only happen by an even number. Now we are ready to move on to skein modules. So we will start with the framing skein module. Let M be an oriented 3-manifold, and consider the R module generated by the set of unoriented frame links in the manifold up to ambient isotopy, where R is the ring of Laurent polynomials in the variable Q. Then consider the submodule generated by the framing expression shown below. That is, the relation between two links with the same underlying unframed link, whose framing differ by 1. Then, the framing skein module of the manifold is just the R module quotient by the submodule generated by the framing relation. So we have the following theorem. For an oriented 3-manifold, the framing skein module of the 3-manifold is equal to the direct sum of an R module generated by the set of links which do not intersect any non-separating two-sphere in M transversely at exactly 1 point, where R is the ring of Laurent polynomials in the variable Q. This direct sum is of the direct sum over links which do intersect a non-separating two-sphere in the manifold transversely at exactly 1 point. So a summary of the proof is as follows. First, we will consider links which do intersect a non-separating two-sphere in the manifold transversely at exactly 1 point. So we will let Ki be a component which intersects the non-separating two-sphere at 1 point. Then the Den homeomorphism, which changes the framing of Ki by 2 full twists, is ambient isotopic to the identity, and this is due to our main result. This gives a relation q squared minus 1 of our link is equal to 0. So when we quotient our R module by this relation, we have our desired result. Now for links which do not intersect any non-separating two-sphere in M transversely exactly 1 point, we have two cases. We have either it doesn't intersect at all, or it intersects more than twice. And in this case, there is no relation. You cannot change the link by ambient isotopy, the framing of the link by ambient isotopy. So we want to consider the case when the link intersects the non-separating two-sphere in 2 points. Now the skein module does not distinguish components. So recall that when we looked at the Dirac trick, you change one component by a +2 and a different component by a -2. But since the skein module does not distinguish components, this cancels in the skein module. So you have no relation via ambient isotopy, or it doesn't show through the skein module. Next, we have the following corollary that states that there exists an epimorphism we call omega from the skein module, from the framing skein module to the group ring over the first homology of the manifold with Z2 coefficients. This epimorphism is not canonical. It depends on the choice of spin structure. We will use the homomorphism that I described before to construct this epimorphism. So let K be a frame knot in the manifold. Then we will consider B to be the homomorphism described before, and we'll let if B evaluated by the homology class of K is equal to 0, then we will let omega K equal the homology class of K. If B evaluated by the homology class of K is equal to 1, then omega K will be equal to Q times the homology class of K. Next, we will discuss the Kaufman bracket skein module. So let M be an oriented 3-manifold, R a commutative ring with unity, and A fixed invertible element in R. Then we will consider the R module generated by the set of unoriented frame links in the manifold up to ambient isotopy, and the submodule generated by all local skein expressions of the form shown below, where L plus, L0, and L infinity are identical except in a small 3-ball, and the difference is shown below. Then the Kaufman bracket skein module is defined by the following. It is the R module quotiented by the submodule generated by the skein expressions. So notice that we have the following relation. That is the relation between two links with equivalent underlying unframed link, where the difference is in the framing, and the difference is by +1. And we will call this the framing relation. We have the following proposition That is, there exists an epimorphism, we'll call this phi, from the Kaufman bracket skein module to the group ring over the first homology of the manifold with Z2 coefficient. This epimorphism, like the one that we discussed in the framing skein module, is not canonical. It also depends on the choice of spin structure on the manifold. The codomain of this epimorphism we will call spin-twisted homology. Next, we will discuss the Q homology skein module. Let M be an oriented 3-manifold, and then consider the R module generated by the set of ambient isotopy classes of oriented frame lengths in the manifold. Then consider the submodule generated by the skein expressions shown below. So for this first skein expression, L plus and L naught are identical except in a small neighborhood where they differ in the following way. So L plus has a crossing and L0 is a smoothing. The second skein expression is identical to the one we've seen in the framing skein module. L1 and L have the same underlying unframed link, and their framing differ by 1. The Q homology skein module is the R module quotient by this submodule generated by the skein expressions. So the last proposition that we have today is the following. There exists an epimorphism between the Q homology skein module and the group ring over the first homology of the manifold with Z2 coefficient. Just like the other epimorphisms that we've seen, this epimorphism is not canonical and depends on the choice of spin structure on the manifold. So now we're going to end with a diagram summarizing the corollary and propositions. So first we start with the Q homology skein module. As I stated before, there exists an epimorphism between the Q homology skein module and the group ring over the first homology of the manifold with Z2 coefficient. This depends on, it's not canonical, it depends on the parallelization of the manifold, which is related to the spin structure on the manifold. So that's what you're seeing here. Then you have the framing skein module. As I stated before, there exists an epimorphism between the framing skein module and the same group ring over the first homology of the manifold with Z2 coefficient. This again depends on parallelization, which is related to spin structure on the manifold. Finally, we have the Kaufman bracket skein module. And as I stated before, there exists an epimorphism between the Kaufman bracket skein module and the group ring over the first homology of the manifold with coefficients Z2. There's a few other mappings here. So you can go from here to here with a change in variable, negative a cubed. So Q changes to negative a cubed. And then also here. And this is coming from the spin structure, where we explain that this here are elements of the cohomology of the manifold with Z2 coefficient. Thank you.